In this week, we'll take a look at the ideal gas law, and this is primarily a review from your freshman year. This is going to be PV equals nRT. The first assignment is mostly some basic gas law questions and a few conceptual questions. The ideal gas law is PV equals nRT. P stands for pressure and may be any pressure unit that we've used so far, from atmospheres to kilopascals to millimeters mercury or torr. V is volume, and unlike the combined gas law, where we can use any volume as long as they match, here we must use liters. This is primarily due to the R value being listed in liters as well. N is new and stands for the number of moles. R is a gas constant, and we have several that will match the individual pressure units. And then, of course, there's temperature, which must still be in Kelvin, given the fact that 0 and negative Celsius will mess up the formula. The important difference between the ideal gas law and the combined gas law is this is not how a gas changes. This is a gas in its current conditions. It's extremely powerful and also very useful when it comes down to stoichiometry and calculating the various features of a gas. It's pretty easy to measure the pressure, volume, or temperature of a gas if you have the right instruments. With that, we can calculate the number of moles, and then from moles convert to grams. This is useful because we can't actually measure a gas on a scale. Or, in a stoichiometry example, if we calculate and we know how much of a product will be made and how many grams of the product will be made, we can predict how much space it's going to occupy or how much pressure it will exert. In my classes in your freshman year, I demonstrate this with the airbag lab, where I have you calculate the amount of grams and then eventually moles of carbon dioxide that's going to be produced in a basic reaction. And then I have you figure out if it's going to fit into a plastic bag or not. We need to discuss the number of moles variable because this is a pretty important variable and also new with the ideal gas law. And it just represents the number of moles, but it's far more powerful than you may realize. There's a formula hidden within that. If you go back to our basic mole conversions, we know that moles is equal to the mass of the substance divided by the molar mass of the substance. This means you can actually insert this formula within the ideal gas law. And that means you can solve for the mass of the gas or the molar mass of the gas. If you don't know what the gas is, you can calculate molar mass and possibly identify it. If you don't know how much it weighs, you can calculate the mass because you can't use a balance. So number of moles is actually an extremely useful variable. I'm going to do a couple examples today on the ideal gas law. In your first assignment this week, this is actually a review from your freshman year. Let's take a look at the formulas before we take a look at problem number 1. The ideal gas law is pressure times volume equals number of moles times the gas constant R times the temperature. Remember, this is not a change in pressure, volume, or temperature. This is a gas as it currently is. And one of the best ways to identify the ideal gas law is the fact that it includes the number of moles. If you're ever asked or given anything to do with moles, it's probably going to work with the ideal gas law. We also can read through the problems and notice that nothing is actually changing. There's no change in pressure, there's no change in volume, and so forth. Unlike the previous laws, we are a little bit restricted by what units we can use. This is because of the R value. And there are many R values depending on the pressure that you use. But every single R value uses liters as its volume. It uses Kelvin as its temperature, but that's a standard for gas laws anyways. Of course, it uses moles, and then the pressure will change. You might be using kilopascals, atmospheres, torr, etc., and that's why the R values themselves change. A few other points. STP, it stands for standard temperature and pressure. The temperature happens to be 0 degrees Celsius, and the pressure is 1 atmosphere. If you ever see the conditions STP, make sure that you know that these are the temperature and pressure that are given to you. Let's begin by taking a look at problem number 1. Calculate the volume 3 moles of gas will occupy at 24 degrees Celsius and 101.3 kilopascals. I teach my freshmen to identify all the units and write them down so they know what they have and making sure the units that are given are appropriate. So going through this, it says calculate volume. Well, that sounds to me like we don't know what the volume will be. 3 moles, that sounds like N. will occupy at 24 degrees C. The temperature is 24 degrees C, but I also know that I cannot use Celsius. Remember, to convert Celsius into Kelvin, you have to add 273 to it. When you add 273 to this, you end up with 297 Kelvin as our correct temperature. And the final unit given to us is 101.3 kilopascals. That's going to be our pressure. Our pressure is going to dictate our R value. Because this is given in kilopascals, I must use the kilopascal pressure, or R value, which is 8.31. Both the R values given this assignment are rounded a tiny bit. The full value is 8.314, and the R value for atmospheres is actually 0.08206. We can use the rounded version for this exercise, although either will suffice. So because our kilopascals are here, we need to use the R value with kilopascals, 8.31. We also notice that there's kilopascals, there's Kelvin, there's mole in our R value, and we notice that liters is our volume. So whatever we solve for, our volume must be in liters. Now I can plug this in and solve. Pressure, that's been identified, is 101.3 kilopascals. Volume, we don't know. We can leave that as simply V. N is number of moles, so we have 3. The R value for kilopascals is 8.31. And the temperature in Kelvin is 297. Easy enough to solve for V. Divide both sides by 101.3. Plugging this into a calculator, we know that volume equals 73.09 liters. In the second example here, going directly to number 2, how many moles of a gas will be present in a gas trapped within 100 milliliter vessel at 25 degrees Celsius at a pressure of 2.5 atmospheres? Here we're looking for moles. So going down here, identifying what units we see as I read this. N is unknown. 100 milliliters sounds like the volume. 25 degrees Celsius is the temperature. And the pressure is 2.5 atmospheres. Before I go ahead and plug in my units into my ideal gas law formula, I need to double check my units. For example, the volume is given to me in milliliters, and I know that the R value is always listed in liters. This is impossible to use. So converting milliliters to liters is easy enough problem. If you take 100 milliliters, divide by liter, convert to liter, milliliter, convert to liter, you know it's 1 to 1,000. This ends up being 0.1 liters. Temperature we know is impossible to use. We can't use Celsius, we must use Kelvin. So you add 273, and that is 298 Kelvin. Atmospheres is okay. We do have an R value for atmosphere. According to the previous information on this page, the R value for atmosphere is 0.082. And so we can keep using atmospheres. Now that we have the correct units, we can plug it into the ideal gas law. Pressure is 2.5 atmospheres. The corrected volume is 0.1 liters. Number of moles is what we're seeking. We'll leave that as N. R value for atmospheres is 0.082 according to the constant on this paper. And then the temperature is 298 Kelvin, not using Celsius. Solving for N, divide both sides by 0.082 times 298. Remember to be careful with your order of operations. When you actually do this and you cancel out the numbers that are on the number of mole side, it's still product of the top divided by product of the bottom. This tends to be the number one problem I see as an order of operations issue with students. So when you multiply 2.5 times zero point 0.1 and you get a single answer, you divide by product at the bottom, which is 0.08 times 298. Make sure you keep track of your order of operations. When you resolve this, the correct answer you should get is N equals around 0.1 moles total.